everyone, myself Neha Shah from LG Institute of Engineering and Technology from the Department of Electronics and Communication Engineering. Today I am going to explain you three topics. The first one is Fourier series, the second one is waveform symmetries, and the third one is calculation of Fourier coefficient from the subject of signal and system from the third unit, which one is Introduction to Fourier series and Fourier transform. So starting with the first topic, which one is Fourier series. First of all, what is Fourier series? What are the requirements of the Fourier series? So starting with the first topic, which one is Fourier series, it is the tool used to analyze any periodic signal. Basically, if you want to convert any signal from time domain to frequency domain, so for that we are using either Fourier series or Fourier transform. If the sequence will be in the form of periodic signal, then we are using the series. And if the signal will be non-periodic form, then we are using the transform. And as you know that the transform techniques are basically used to reduce the complexity of the calculation of the any term. Right. So basically we are using this Fourier series for the analysis purpose as well as for the reduction of the calculation. Now there are basically three types of the Fourier series. The first type is trigonometric Fourier series or quadratic Fourier series. The second one is polar Fourier series and the third one is exponential Fourier series. Now we will see the equations for these three kinds of Fourier series one by one with its coefficient. So starting with the first type of the Fourier series, which one is trigonometric Fourier series. Now, if you are taking the trigonometric Fourier series or quadratic Fourier series, its equation will be like this: x of t equals to a0 plus summation n equals to 1 to infinite an cos n omega 0 t plus summation n equals to 1 to infinite bn sin n omega 0 t. In this equation, a0, an and bn are considered as its constant. So, if we are finding the values of constant, starting with the first term as a0, the value of a0 equals to 1 upon t0 integration t to t plus t0 x of t dt. In this equation, t0 will consider as the fundamental duration which will be in the repeating form. So, instead of t0 we can also take as capital T. And instead of this range t plus t0, we can also take the range of which duration will be in the repeated form, like 0 to t or minus t by 2 to t by 2 likewise. So according to the situation, this term can be changed. Now the next coefficient is an. The value of an equals to 2 upon t0 integration t to t plus t0 x of t cos n omega 0 t dt. So the cos terms means even terms will gives you the constant is an and sin term or odd term will gives you the coefficient as bn. So the value of bn equals to 2 by t0 integration t to t plus t0 x of t sin n omega 0 t dt. Now we will taking the second type, which one is polar Fourier series. So if we are writing the equation for this, x of t equals to c0 plus summation n equals to 1 to infinite cn cos n omega 0 t plus phi. Why? Because as you compare the trigonometric Fourier series with the polar Fourier series, almost these two things will be same except the term this. Why? Because if we are combining the cos term and sin term, basically these two terms will be same, only there will be change in the phase. So if we are combining these two terms, cos as well as sin, in the one only form like cos term, so we will including this phase term. So if we are taking the phase change, so cos term will convert in the form of sin or sin term will convert into the cos term, right? So combination of an plus bn will gives you the cn. Now in this the constants are c0 and cn. So if we are finding the value of c0, the value of c0 will be same as a0 and the value of cn will be considered as under root of an square plus bn square. So after finding the value of a0, an, bn, we can find out the final value of polar Fourier series equation. Now if we are finding the value of phi n, the value of phi n means phase angle of this term will be equals to minus tan inverse imaginary part upon real part, or we can also say that sine term upon cos term. So coefficient of sine term will be considered as Bn and the coefficient of cos term will be considered as An. So the term will be minus tan inverse Bn by An. Now if we are finding for the third type, which one is exponential Fourier series. So for that the equation will be like this in the form of exponential e raised to something. So the equation will be like this: x of t equals to summation n equals to minus infinite to infinite Cn e raised to j 2 pi n t divided by t0. Here the value of Cn will consider as its coefficient. So if we are finding the value of Cn, the value of Cn equals to 1 upon t0 integration t to t plus t0 x of t e raised to minus j 2 pi n t divided by t0 dt. Now there will be some condition for the existence of the Fourier series. These conditions will be considered as Dirichlet's condition for the existence of Fourier series. If we are defining this condition, the first condition is the periodic signal x of t and its integrals are finite and single value. Means the value of it should be finite as well as single value. For any particular one thing, only the one value should be there. In the interval of t to t plus t0, it means over a one finite period of time called t0. Now the second condition is x of t must have only finite number of discontinuities in the given interval of time. So it should not be more discontinuous in the given particular time duration. Then the third condition is x of t must have only finite number of maxima and minima in the given interval of time. It means it should have finite number of maximum value and minimum value of the signal in the given duration of the time. And the fourth condition is the function x of t should be absolutely integrable. It means integration over minus t0 by 2 to t0 by 2 more x of t dt, this should be less than infinite. It means it should be some finite value. If this four condition will satisfy, then and then only the Fourier series can exist, otherwise it can't exist. Now the next topic is waveform symmetry. Now if we are finding any Fourier series coefficient, there will be different coefficients. Like suppose if I am taking trigonometric Fourier series, so for that we have to find out a0, an, bn, right? So for each and every example we have to find out a0, an, bn. So for reduction of calculation we will using this waveform symmetry. In the waveform symmetry we will check whether the given signal is odd signal or even signal, and based on that odd or even symmetry we can just find sum of the coefficient of it, and from that we can solve the example. So basically this waveform symmetry will be used to reduce the complexity of the mathematical calculation of the Fourier series. So starting with the waveform symmetry, if the given waveform has some kind of a symmetry, then it becomes easy to calculate the Fourier coefficient. It means to find Fourier coefficient in the easy form, we have to use this waveform symmetry. The first waveform symmetry is signal with zero mean. Now what is the value of mean? Mean means average value. If the signal with the average value equals to 0, it means half part will be on the positive part and half part will be on the negative side. So it will give you the on an average equals to 0. So this kind of signal will give you the signal with the zero mean. Now suppose this kind of signals will be there, then it will consider as if the mean value of a given signal is 0, it means integration 0 to t x of t dt equals to 0. It means if we are integrating this signal, its value will becomes equals to 0. Then the value of a0 equals to 0 means there is no need to find out the value of coefficient a0 because the value of a0 will equals to 0. Now the second waveform symmetry is even symmetry. Now what is the even term? If the given signal x of t is an even signal, then the condition will be like this: x of t equals to x of minus t. So for that, the value of Vn equals to 0 for all the values of n. Means odd terms coefficient will become equals to 0. So there is no need to find out the coefficient of Vn. Now similarly it will taking the next symmetry as odd symmetry. So for the odd symmetry, for the given signal, the condition will be like this: x of t equals to minus of x of minus t. So this kind of condition will satisfy for only the odd signal, and if the odd symmetry or odd signal are given to you, then you have to take the value of a0 as well as an equals to 0 for all the values of n. So there is no need to find out the coefficient value of a0 and an. Just we have to find out the value of Vn, and after finding the value of coefficient of Vn, will putting the value of Vn in the equation of x of t to find out the final answer of the Fourier series. Similarly, the fourth symmetry is half wave symmetry, means half wave will be symmetrical. So for that, what will be the condition? If the given signal x of t has half wave symmetry, it means x of t equals to minus of x of t plus t0 by 2, means half wave will be symmetric. Then will taking a0 and an equals to 0 for all the odd values of n, and the value of Vn equals to 0 for all the even values of n. So it will apply this waveform symmetry in the process of finding the coefficient of the Fourier series a0, n and Vn, then the number of coefficients will be removed. It will apply this symmetry. So this way we can reduce the calculation of the Fourier series coefficient. We'll apply this all the rules in the calculation of the Fourier series examples in the next section. So in the next session, I will start with the first type of the Fourier series, which one is trigonometric or quadratic Fourier series. So we'll solving some examples based on this trigonometric Fourier series, and in the further sessions we will covering the exponential Fourier series and other one. Thank you so much.